Ben hazırım.
Dear guests, welcome to our seminar organized by the Istanbul branch of the Turkish Chamber of Civil Engineers. Today we are holding the second of international seminars. The seminars aim to bring together prestigious engineers, academicians and experts from all around the world with you. The seminars, which will be published on eğitim.imoistanbul.org with the option of original language and the Turkish translation, will convey to you the new technologies and important research about our professions in the world. The topic of our seminar today is Multiscale Discrete Image Theory, a novel approach for multiscale modeling of failure in heterogeneous materials, and its lecturer, Professor Caglar Oskay. The seminar is going to be moderated by Assos Professor Dr. Murat Serdar KIRÇIL. We would like to thank Mr. KIRÇIL for his moderation and Mr. Oskay for his presentation in advance. You can send your questions from the live chat of YouTube and our education system. Now I'm going to hand you over to dear Mr. KIRÇIL.
Thank you very much, Damla. Dear colleagues, good evening. Welcome to international seminar organized by Turkish Chamber of Civil Engineers, Istanbul branch. Caglar Oskay from United States is with us this evening. He is professor at Vanderbilt University. He will make a presentation this evening titled as Multiscale Discrete Damage Theory, a novel approach for multiscale modeling of failure in heterogeneous materials. I would like to thank Professor Oskay for his contribution. I also would like to extend my thanks to you all for your participation on behalf of Turkish Chamber of Civil Engineers, Istanbul branch. Before leaving him the microphone, I would like to read his short biography. Caglar Oskay is Professor of Civil Engineering and Environmental Engineering and the Mechanical Engineering departments at Vanderbilt University. He very recently returned to Vanderbilt from his service as Program Director of the Engineering for Civil Infrastructure Program within the CMMI division at the National Science Foundation. He graduated from Middle East Technical University in 1998. He received Master of Science degree in Applied Mathematics and Master of Science and PhD degrees in Civil Engineering from Rensselaer Polytechnic Institute. His research focuses on nonlinear response prediction of heterogeneous materials and structures using computational modeling and simulation. His recent research includes characterization of the failure response of systems that involve multiple temporal and spatial scales, computational method development, and reduced order modeling for composites, polycrystalline materials, and metamaterials subject to fatigue, impact, blast, and other extreme loading and environmental conditions. Dear Professor, from now on, the microphone is yours.
Thank you very much. Let me share my screen. And I'll make this big. I hope All right. I would like to begin by thanking Professor KIRÇIL for his kind introduction, and also Damla Altıncı for inviting me for this very nice lecture series. I really appreciate, and I'm always happy to talk with my Turkish colleagues. I'm really glad that I get a chance to do so today. And I also would like to thank my graduate student, Zimu Su, who has been doing what I'm going to talk about today. He's really the one who's driving just about most of the research that I'm going to be talking about today. So the title, Professor KIRÇIL already mentioned. So we're going to be, with this area of research we have been working on, particularly multiscale discrete image theory, is something that we have been working on in the past 2 or 3 years. And it is, we have been getting some very, very nice results, and I will be sharing some of that with you today. And in particular, the application of it to multiscale modeling of failure in heterogeneous materials. As you know, there are various different types of heterogeneous materials. We will be particularly focusing on fiber-reinforced polymers. But the general application area and applicability area of MDDT goes beyond that, and potentially, for example, other heterogeneous materials. Many of you are familiar with concrete, for instance, modeling, multi-scale modeling of concrete, and so on, could also be done with this type of theories. And the reason that we're focusing particularly on these materials is because of our partners and funding agencies such as the Office of Naval Research and AFRL are quite a bit interested in this type of research and fiber-reinforced polymer materials in general. Here's a brief outline of the presentation. I will begin by objectives, defining the objectives, some background information, and I will basically tell you why we do what we do. I'm actually going to spend a good bit of time there, simply because of the fact that this is an academic talk, and I understand that we're looking at a wide range of folks and a lot of practitioners who would like the general impact areas of the research as opposed to very specific details. I do have some details. There are some equations. Bear with me. They will all pass, and I'll try to accelerate my talk a little bit during that period and try to focus more on the applications and the results as opposed to the theories. So, but I will introduce the multiscale discrete image theory, and also I will particularly focusing on addressing one important issue that has been dogging failure modeling for quite some time. That is addressing the spurious mesh size sensitivity of models that try to predict damage and failure in composites and other materials. We will be generalizing the MDDT after giving you the theory to cracks, macroscopic cracks that are in arbitrary orientations or potentially reorienting cracks, and also extended to fatigue. So composite materials are quite ubiquitous these days. You can find application of these in various different industries, starting from aerospace to automotive to renewable energy to civil infrastructure. They're all, for example, in the aerospace in the past 20 years or so, there has been a really revolutionary improvements and in terms of use of composite materials. All the new aircraft structural components are primarily made of composite materials, or at the very least, the majority of them are made of composite materials. And therefore, of course, they're more on the high quality composite materials side, carbon fiber reinforced thermosets and thermoplastics and so on and so forth. In view of the fact that a lot of these materials were originally fairly expensive, it took a little bit more time for the materials technology to get into the automotive sector. But now, after several years of research in reducing the cost of these materials, now fiber reinforced composites are becoming also a part of the automotive industry. Not just the exotic automobiles like Lamborghini and such, which have been using this technology for quite some time, but more on the more popular and more widely used cars as well are going to be using this technology. Renewable energy, in terms of wind turbines, the primary structural components of wind turbines, the blades and so on, have been made by fiber reinforced unitary fiber reinforced composite parts. And therefore, and given that the clean energy is among the priority areas for the United States and the world in general, It's just the use of these materials will continue to grow. The same thing is true for civil infrastructure. Because of the cost limitations, the incorporation of fiber reinforced polymers to civil infrastructure has been relatively slow compared to, say, aerospace or renewable energy. But they are coming along. A lot of activity going in that direction, and there are several legislation at the moment that is being considered in the U.S. Congress that will provide additional funds and resources for research and also incorporation of these materials into civil infrastructure. An example here, the picture that I'm showing here is from a patch application. That is probably one of the more commonly, oops, I'm sorry. Can you still see? Let me just end the show and restart. Okay, I hope everybody can still see it. I was trying to get to the pointer here. And so this is a patch repair application. There are various different, more niche applications in civil infrastructure, but that will also likely to grow. My own research and the research that we conduct at our laboratory has been primarily focused on the high-performing structures, and the high-performing structures are those that operate at or near their design limits. And what we have been doing is to develop multiscale and modeling and simulation technologies and techniques that hopefully will allow the incorporation of these materials, as well as accelerate design, certification, and qualification of structures made of these materials using it through a new paradigm. This new paradigm is essentially design, certification, and qualification driven by computational simulation. The figure on the left-hand side here is basically a testing pyramid that is necessary to certify and qualify an aerospace part, and which basically shows that you start from coupon testing. These are standard, test articles, and you need to do thousands of these tests before you can fully understand the material behavior, and then slowly progress upwards to more and more complex, complicated structural features, all the way up to the full component testing. And this is a significantly onerous testing platform and testing requirement in order to certify a structural part. So one will, the coupon testing is fairly straightforward. There's really not necessarily a whole lot to gain in that direction. Component testing all the way at the top of the pyramid, those are tests. There are very few number of tests that a certification engineer will have to do anyway, and they will not necessarily give up on that. But this mid-scale, the middle of the pyramid, where you go from element testing to subcomponent testing, is extremely complicated and extremely expensive, simply because of the fact that you're really dealing with different types of boundary conditions, different types and shapes of structures, and testing these structures is not an easy endeavor. So the idea when it comes to modeling and simulation-based design, certification, and qualification paradigm, the idea is to eliminate, or at the very least to reduce the testing requirements and perform these processes primarily based on computation as opposed to primarily based on experiments. They're not going to go away either way, but we hope to be able to reduce the testing load as much as possible. In addition to that, multi-scale modeling and simulation, because it connects the material to structure, is a really an important paradigm for materials innovation, in the sense that how can we improve the microstructure properties, for instance, to achieve structural components that perform better and more efficiently, and so on and so forth, for their designed application. And also it allows us to perform long-term durability and maintenance analysis that also has significant impact on these systems. All right, so in terms of multiscaling, what is multiscaling? What are the types of multiscaling approaches that are available currently today? And, ultimately, how can we model these heterogeneous materials and how structures made of heterogeneous materials? So the simplest way to go about doing this is what we call direct numerical simulation, in which you consider a structure, for instance, and that structure is composed of some sort of a heterogeneous materials. And let's assume that we have the ability to resolve every single little piece of information from the microstructure throughout the entire structural domain. If you can do that, then we can use, for instance, standard tools like finite element analysis techniques, and provided that we have the appropriate constitutive models that describe the failure behavior of the material constituents, you can essentially, model everything in detail and perform your simulations, get the results, and they constitute the truth model, provided that you use the appropriate level of resolution necessary to track all the failure processes. This type of an approach, direct numerical simulation, provides accurate description of the overall structural response and also the local response metrics and local response behaviors. However, computationally, they are obviously quite intractable. It is very difficult to run these type of simulations beyond very small coupon type analyses. And so it doesn't really go beyond academic exercises or understanding of mechanisms that are associated with the failure processes. The second approach that I'm listing here is sequential multiscale modeling. This is perhaps among the most commonly used multiscale approach. In this case, we are thinking about the material and the simulation of a material and the simulation of a structure somewhat separately, but connected in a one-way fashion. We start with defining a characteristic volume. This is a microstructure volume. It's a small volume in which the microstructural features are resolved. And this could be a representative volume, a statistical volume element, or a unit cell. And we perform a large number of simulations under different loading conditions and so on and so forth to understand the behavior of the system. For instance, evolution of strength as a function of different load directions, and create response surface, either using something like a metric constitutive model. One could calibrate the material properties or model properties that can represent this in a much condensed form using some sort of a macroscopic constitutive model. And then we kind of throw away the microstructural analysis and go to a structural level analysis in which this macroscopic constitutive model serves as the material model, and we perform structural simulations through this approach. Naturally, this is barring the training part, which could be quite expensive, the structural analysis part is computationally quite efficient, and it provides accurate description of the overall macroscopic structural response fields. Capturing the local response fields are a little bit more complicated now, and it's still an ongoing research topic. And it is not as easy to retain that local information, which is very important for things like failure initiation. The third approach, this is the concurrent hierarchical multiscale modeling approach, is another paradigm in which the microstructure simulation performed over the characteristic volume and the structural simulation performed over the structure itself are fully coupled to each other and evaluated or simulated concurrently. And they're basically coupled to each other. They feed off of each other. And provided that there are some technical requirements are there, such as the scale separation principle and so on and so forth, these type of approaches have the capability to accurately describe the overall as well as local response fields. However, even though they typically are a little better than direct numerical simulations, they're still computationally quite intractable beyond academic problems. In order to eliminate that or alleviate that computational cost issue to a certain extent, we're going to talk about some reduced order modeling methodologies that we perform to eliminate or replace the microstructure simulations that are very costly with a a simulation that uses a much coarser basis, but still capture the behavior quite accurately. So what are the challenges when it comes to multiscale modeling of failure? That is important. So there are three challenges that I'm listing here that we will be talking about a little bit. One is something that I've already talked about, the computational complexity and length scale. And if you start thinking about fatigue, which is repetitive loads and the behavior of the material under repetitive loads that could be on the order of thousands, tens of thousands, up to millions of cycles. That's how do we deal with the computational complexity of a simulation like that. You don't want to wait for such a long time. As a practitioner engineer, for example, you want to be able to get the results as quickly as possible. The existence and how to define the material microstructure, or the existence of the representative volume concept is a question once the failure processes begin. And also the mesh size objectivity that I will be talking about a little bit more in a second. There has been several different types of multiscale, concurrent hierarchical multiscale models that have been proposed previously. And the list that I have here is based on the type of representation of failure at the microscopic and the macroscopic scales. For instance, the discrete models consider discrete cracks, the actual fracture processes at both scales. The continuum discrete model considers a smeared damage approach at the microscopic scale, but considers discrete cracks and how that fracture, basically the fracture mechanics approach at the macroscopic scales. And a continuum model considers continuum approaches or smeared damage approaches at both scales. What we're going to talk about today, the MDDT, is about representing the microscopic cracks as cracks and upscaling them into a continuum level description or a smeared description of cracks at the macroscopic scale. Now, why is that? And why do we want to do that as opposed to these other types of approaches is because of observations in fiber reinforced materials. So as you can see here on the right-hand side, we do see distinct cracks when you zoom into the material in the order of several, microns. We do see these cracks that are very distinct. However, once you start zooming out from that and look at the laminate scale or the structural specimen scale, you start seeing a significant amount of damage, the discrete representation of which is completely unfeasible, especially once you go even bigger to a structural scale from specimen scale. So therefore, it is very natural for us to consider this to be a discrete continuum modeling approach. The next issue, as I mentioned before, is this issue of mesh size sensitivity. Naturally, when you do an analysis, computational analysis, there will be an effect of how much discretization, how densely you discretize your system to solve. And the accuracy will be affected by that. But this is something, what we're talking about here is something a little bit different than that. And what we call mesh size sensitivity in damage mechanics models refers to the localization of damage to a single element width, if you're using finite element analysis, for example, regardless of the size of the finite elements. Now, this does not necessarily constitute a problem by itself, but what happens is that as you refine the mesh, the energy dissipation, the amount of energy dissipated during the fracture process also asymptotes to zero as the mesh size asymptotes to zero. That's a problem because you basically are not dissipating any energy because of the fracture process. And so this is a common and traditional problem. For static and fatigue loading conditions, the reasons are quite different. In the static loading, the ellipticity of the underlying partial differential equations are lost once you start going into the softening regime. Whereas in the fatigue loading, even at the hardening regime, fatigue models typically demonstrate mesh size sensitivity due to the inability to capture strain singularity. So there has been quite a bit of approaches that attack this problem. What we wanted to do is to make sure that we develop an approach that is valid for multi-scale simulations and valid by leveraging the principles of multi-scale analysis. All right, so the basis of the model, MDDT, is what we call computational homogenization approach. And I'll just kind of briefly give you the flavor of this. We start with a direct representation of the underlying boundary value problem, the partial differential equations that describes the problem. And then we go ahead and split that problem into two separate problems, one defined over the entire macroscopic structure. That's called the macroscale problem. And then microscopic structure defined over the representative volume or a unit cell, and that is called a microscale problem. We solve these two problems in a coupled fashion, in that there is a microstructure associated with each material point. In this case, if you're using finite element analysis to solve the macroscopic problem, at each quadrature point, you associate and track the evolution of damage within a different material microstructure throughout the system. And what happens is that the macroscale boundary value problem evaluates the overall response fields, and it communicates with the solution of the microscale boundary value problem to update the macroscopic stress state. So in this nonlinear analysis, one has to solve two nonlinear problems that are hierarchically coupled at the macroscale and the microscale. So you need to evaluate the microscale boundary value problem at each integration point at every increment of the macroscopic analysis. So it's a very computationally complex problem, is what I'm trying to say. Now let us talk about how we incorporate damage and fracture into this, especially discrete fracture, into this paradigm. So consider a structure that is subjected to some sort of loading. That could be a static loading or a cyclic loading. We will be looking at both cases. And let's say that we incrementally load this system, and at a point in time, this system, at some point in that structure, you start observing cracks. Let us call the first crack that you see is is a matrix crack that occurs, and let's call the morphology of that crack S1. This is, of course, a three-dimensional crack, so if you look at it, you need to incorporate this in a three-dimensional fashion, so you see a surface, that is the crack surface that shows at the microscopic scale. Now, if you continue to load this, there could be another type of loading or another type of damage that could occur. In this case, let us say that nearby this initial crack, micro crack, we start seeing fiber cracking that also starts to develop. Continue to load it. At another point, you have a different crack with a different orientation, for instance. So if you consider this to be a completely random microstructure, in that case, depending on the loading condition and the position, there are infinite number of possibilities of where these cracks occur. We will talk about that too in a minute. But fortunately for us, for fiber-reinforced composites, long fiber-reinforced composites, there are certain orientations and features, crack features that are more likely to occur and more likely to happen, which is an information that we would like to use when we're building our system. So what we do then is now consider the microstructure, not just the geometry of the microstructure, but the geometry plus a series of what we call potential failure paths, like S1 and S2 and so forth, so on and so forth, as the representation of the microstructure. So it is not just the microstructure geometry anymore, but these series, discrete set of potential failure paths. And there are n of them that is available in our microstructure. So then we continue with a microstructural displacement approximation that allows us to write it in a form that takes advantage of these what we call elastic influence function and separation influence function. These are Green's functions that you can solve by offline very quickly using linear elastic analyses defined over the microstructure. Then we do a little bit more math to bring the equilibrium, the microstructural equilibrium, expressed only on these potential failure path surfaces. The T here is traction, the forces that are on those potential failure paths. Delta is the separation. That is how much that crack is, or that potential failure path is separating under the loads. Epsilon bar is the macroscopic strain state, and so on and so forth. So then we perform a coarse discretization of these potential failure surfaces using a coarse number of shape functions, a very small number of shape functions, and we can then bring the system of equations, the microscale system of equations, into a very simple form, where we have this traction, where we are tracking the average tractions over these interfaces and the average separations, in which this is the microscale equilibrium, and we couple it with what we call cohesive models, which describes the progressive damage evolution as you start stretching that interface. And what you end up getting at the microscopic scale is, instead of solving the full nonlinear analysis of the microstructure, you have an algebraic system of 3M unknowns, which you have to solve for. But that 3M is a fairly small number, provided that you incorporate a small number of these failure paths. So that is the idea. And, you have a series of coefficient tensors. These are some tensors, and you can consider them to be constitutive parameters that is computed based on the material microstructural morphology and the crack paths. And they're analyzed a priori. We basically compute those values. After that, it's pretty much a standard finite element analysis, where instead of using a constitutive model such as J2 plasticity model, von Mises plasticity model, we solve this system of equations at the quadrature point. So it's a fairly straightforward system of equations to evaluate. The second interesting question is, okay, how do I define the microstructure to begin with? Because this is, relatively speaking, a random microstructure. So as this is well known, that once you start going into the failure, the RVE concept, the statistically representative volume element concept, is no longer applicable. So it is a question mark as to how I can select a material microstructure. So consider a microstructure and a fracture path that we would like to incorporate. And the microstructure itself is a reasonably sized microstructure, which represents the statistics of the geometry of the morphology correctly. Now, you can double this in size in two directions, make a little larger microstructure, or quadruple this and create another microstructure. And the expectation is that, they are supposed to behave more or less the same way, because, there's no new information that is embedded into that structure. But it turns out that they don't provide you the same response. In fact, considering the periodicity condition that this system is periodic and embedded with a fracture path, the small microstructure is actually equivalent to a larger microstructure in which the crack is also repeated. Now, what you have to consider is the density of those microcracks is in addition to the microstructural geometry. Now, even though these three microstructures are different, lucky for us, we have analytical relationships that relate the reduced order model, the MDDT model, associated with a small microstructure to a larger microstructure as a function of its size. So we have very nice analytical approaches to connect them. Now, we haven't answered the question yet, but this is something that we are going to use in the next slide, and that will collectively answer this question, is how to pick the appropriate size. The second issue is the regularization to ensure mesh size objectivity. Now, some of you may be familiar, those who are working with concrete materials may be familiar with the classical crack band approach, which was proposed originally by Zdeněk Bajant and co-workers to have a engineering type solution to this regular mesh size sensitivity problem. We will follow a similar path in that in the classical, we will use a classical FE in the macroscopic scale, and we will allow the element size, the failure to localize to an element size. In the classical crack band approach, what you do is you define the constitutive parameters as a function of the element size in such a way that the overall energy dissipation remains constant regardless of the size of the finite elements. Now, the problem here is that you need to adjust the material parameters. The question is, what kind of material parameters do we need to begin with then? So in our approach, what we do is let's keep the constitutive parameters, which are the traction, separation, behavior, the same. What we're going to change is the size of the microstructure as a function of the size of the finite element that we're using. And we can do that very easily because of the analytical relationships that we have observed previously. By this approach, we're going to again keep the overall fracture energy constant by automatically adjusting the size of the microstructure as a function of the size of the microstructure as a function of the element size. So the question to the previous, or the answer to the previous question was, it's essentially an adjusted microstructure. The size is adjusted as a function of the microstructure size, which happens to alleviate the mesh size sensitivity issue as well. So an example, so in this case, we're looking at an open hole specimen with a 090 configuration. An open hole specimen means that you have a hole in the middle of a specimen. It's a flat specimen. 090 indicates that the zero layer has fibers that are oriented along the direction of the loading. And the 90 plies are where the fibers are oriented perpendicular to the direction of the loading. So they're basically cross fibers or cross ply laminates is what we call. And we are running simulations with various different mesh densities, quite intense mesh densities. And if you don't use the regularization approach in the MDDT, you see a clear variation of the strength prediction as a function of the mesh size. It's more or less a linear behavior. Once you apply our scaling, the proposed regularization strategy, you basically are obtaining a more or less constant strength predictions regardless of the mesh density. Even more important, and let's dive into a little bit more as to how the damage is progressing under these. And what we're showing here are 3 different rows with 3 different simulations with 3 different mesh densities, the coarsest to finest from up to bottom. The first is the 0-layer fiber fracture. We are modeling the same, multiple different fracture model failure mechanisms using the MDDT approach within the same simulation. But in this case, we're plotting the 0-layer fiber fractures, 0-layer matrix cracks, and the 90-layer matrix cracks. So if we're just going to show the simulations and the overall behavior, as you can see, though there is no, the behavior is essentially indistinguishable for the 3 different meshes in all different kind of failure behaviors. And the overall failure cracking patterns also align pretty well with the model, with the experimental observations. Here, for example, the 0-layer matrix cracking refers to this horizontal crack that we observe, and this 90-degree layer matrix cracks are these the diffuse representation of these cracks that you're seeing in this north-south direction in this little experimental figure. What can you do with these type of materials? So one of the nice things about the MDDT approach is now we're directly embedding the material microstructure. So the microstructural features start to affect the overall response, and the geometry of the microstructure start to affect the overall response. Here, for instance, we're showing the differences between a square unit cell and a hexagonal unit cell, where the hexagonal unit cell, the crack needs to be necessarily tortuous compared to a square unit cell, which could be very flat. That means that the size of the the amount of area that the crack needs to go through is larger. Therefore, it leads to a larger energy density as well as the dissipated energy, as well as the strength of the system. So that allows us to consider the effect of microstructure in the model. Connected back to what I was saying at the beginning is the ability to innovate material microstructures that will behave well depending on what kind of property that you see in the structural scale. Let's go beyond the potential failure paths idea. So this is the second part of the presentation. One of the things that we have assumed is that we've assumed the orientation. We know the orientations of these potential failure paths. So in general, once you start going into slightly more complex composite structures, such as this rotor assembly right here, where you have a ply drop in the system that goes from a thick panel to a thin panel. There's necessarily going to be additional complications, and the behavior is going to be quite a bit more complicated. As you can see, there's crack merging, crack splitting, and different cracks on different orientations that need to be taken into account. This is a delamination migration test, which is something that we're going to analyze in a second, but it also kind of idealizes the problem a little bit and shows a nice migration behavior that we're interested in quite a bit as well. So the point is that the crack orientations may not always be known a priori, particularly for matrix cracking. And, you can, what we would like to be able to do is to model the crack reorientations in a fairly effective, computationally efficient manner. And we would also like to be able to then extend our approaches to interacting crack networks, hopefully. So how can you deal with this problem? The one strategy that you can do is to apply using the classical MDDT, what I've talked about before, but considering many, many different failure paths and incorporating many different failure paths in the system. Now, this is, you select a large number of a priori failure paths. The issue is that as you select more and more number of failure paths to better capture the crack reorientations, the cost of the simulation also increases, because that 3M, in that 3M system of equation, the M increases. And this is a dense system of equations, so the evaluation is order M cubed, which means that it takes, it scales not very favorably with the increase of those failure paths. Another simple idea that we have come up with is leveraging the rotational invariance of the microstructure when it comes to matrix cracks, which means that if you consider a rotationally invariant microstructure, instead of rotating the crack, what we can do is to rotate the microstructure along the invariant planes. And if that is the case, then instead of incorporating multiple failure paths, we can deal with only incorporate a single failure path in that invariant plane and simply deal with the orientations. And that could be very simple transformation of the reduced order model to the appropriate orientation. So there are two pieces of that puzzle. One is, the expression of the traction as a function of the orientation of the crack, and then define at which point the crack will nucleate so that we can assign the correct orientation to a given material microstructure. For that, we need to incorporate also a failure criterion. And this ellipsoid here tells you the traction state on that traction separation curve, where the traction state is as a function of the orientation. Naturally, the most critical one that reaches the failure criteria first is the one that will initiate, or is going to be the orientation that we essentially take. And there's also some additional work that one has to do, because you need to do this in a discrete way, and you don't always capture the contact point very accurately in a discretized system of equations. Therefore, we do a little bit more work to characterize that orientation accurately. So we have conducted some interesting studies to understand the mode of failure based on this approach, where we are looking at microstructures and loading it in different load orientations in multi-axial conditions. For example, we're showing 3 different types of loads. These are in plane that induces cracks, matrix cracks. And as you can see, what we have found is that most of the failures that we've observed in in-plane loading conditions have been mode 1 separation failures. Now, if you start incorporating out-of-plane load failures, then what we have found was that it was possible to create mode 2 failure criterion as well as mixed mode failure criterion. But note that in these cases, what we're looking at is an orientation of the failure planes only. If you start looking into other directions, we start observing that there are possibilities of mode 1 failure cracks as opposed to mode 2 failure cracks that we have found as well. So one has to be a little bit careful, and hybrid strategies, this calls for a hybrid strategy where you need to have some failure planes that are incorporated into the model in the off axis, and the primary failure plane that will be able to capture by rotation idea. So this, by the way, this is physically very feasible. These two failure paths that, the one thing that you're seeing, this red, the lower right-hand side figure shows a fracture plane that is a mode 1 fracture that occurs actually a little bit earlier than the ones that we are predicting, and that is a plane that is that's crossing the fibers, bridging the fibers. Now, these two failure planes are actually very easily observed in experiments as well. This is a splitting crack. The pure mode 2 failure is a splitting crack that occurs, and the mode 1 failure that we're observing is the matrix shear that are observed in between fibers. So those are all possible modes that are observed in experiments. Now let's go to the modeling of delamination migration. This is a good validation study for us because it also is a fairly, even though it looks fairly straightforward because of the instability of fracture, it's a fairly complicated phenomena. And this delamination migration setup, I believe, was invented at NASA Langley by James Radcliffe and co-workers. And the way that is done is that you have a specimen that is put on here. You basically apply a tension load from the top at a distance L from the tip from left end of the specimen, and you insert a pre-crack. And the pre-crack at a 0-90 interface. And the expectation is that once you start loading it in more or less mode 1 direction, the crack is going to horizontally propagate through that interface. What happens, though, is a little bit different. What you see is that crack propagates a little bit, turns, goes into the 90-degree layer, hits the 0-degree layer up top, turns again, and propagates in the interface that goes a little bit above what it started with. What we would like to do is to be able to model this, and we have used the MDDT approach to characterize this. And as you can see, in different, one thing is varying in these 4 different figures is the position of where we're applying the load. Depending on where you apply the load, you get different force. The behavior is basically a little bit different, but the idea is that the experiments, the simulations that we're showing is very accurately, or fairly accurately, I should say, capturing the experimental behavior and also capturing the fracture propagation quite well. And this was good news for us. We wanted to look at it in a little bit more detail. So what we are seeing here is we're going to see some simulations here, but a discussion of how the fracture propagates. And what you're going to see is that the fracture will not propagate until you get to the strength of the lamina. And then this is going to start, we're going to go down on the force displacement curve, during which the delamination propagation occurs. Then we hit this point after this point 1, after which the material starts to gain a little bit strength again. And during that time, a fracture process zone forms. And by the time you get to 2, the delamination process starts and ends quite quickly. And finally, the second drop is associated with the delamination migration again. And let us look at, I'm sorry, the last figure is not working again, but let's see. Yeah, it's working now. You see the crack starts to propagate, stops, and migrates and cracks again. So we have been able to capture this pretty well and pretty accurately, and also the evolution of the migration distance as a function of load offset is very much in line with the experimental observations. Last piece, I'm going to go pretty quickly. We're at the around 38-minute mark. I don't want to overstay my welcome here. So I'm going to go quickly, but what we're seeing is another important aspect of prediction, which is prediction of failure under fatigue loading conditions. So our objective is to establish or extend the capabilities of MDDT for long-term performance prediction of composite materials, and also gain understanding of what is going on and how the different failure modes that we can represent are interacting with each other. So in this case, we have another additional problem is to how do I deal with, in an efficient fashion, the multiple, potentially millions of cycles that I have to traverse through in time. So even one analysis where you are pulling the analysis is quite expensive. Now consider an analysis where you pull, unload, reload, unload, and continue that a million of times. So what we are doing, the way that we are dealing with this is to consider the time scales to be another multiscale approach or multiscale system where we define a macroscopic coordinate, what we call a macrochronological coordinate, that tracks the evolution of damage in long time scales, and a microchronological coordinate, tau, that tracks the behavior within a single load cycle. And we consider similar strategies to deal with the time scale problem compared to the spatial scale problem, and ultimately we combine the two together. So one of the things that is very important to notice is the distinction between the mesh size regularization, or the reason for the mesh size sensitivity under static and fatigue loading conditions. And we have noted that the regularization premise that we have incorporated into MDDT was the energetic consistency in the softening regime and the selection of the material microstructure in the softening regime. In the classical fatigue-sensitive cohesive laws are typically based on additive consideration, where the static damage and the fatigue damage are considered separately, in which the fatigue damage is related to the number of load cycles that are applied to the system, and or an integrated scheme where the fatigue, both the static and the fatigue damage is considered in a unified fashion. Either way of these approaches, what you observe is a quick shakedown of the nonlinear regime, and basically the damage propagation in a more or less linear hardening behavior. In that case, what happens is that the strain singularities introduce an additional complexity and does not allow the regularization, standard regularization schemes to work effectively in objectively eliminating the mesh size effects. What we have done is to consider a different type of cohesive constitutive law, in which the general stiffness reduction is performed for the static case in the standard approach, like we do in the additive and integrative models, but the fatigue and the fatigue damage effectively affects evolves the ultimate strength and ultimate traction of the domain. By this approach, we allow the system to dissipate energy under fatigue loads in the softening regime, thereby allowing us to regularize the system. So the selection of the cohesive zone model, or the cohesive element, or I should say cohesive law, is very important for fatigue. We have, I'm not going to talk about the general machinery of the simulations, how we solve, but generally speaking, what we have is now, in the case of this time marching or fatigue loads, we have two different systems of equations that we're solving. One system solves the overall response of the structure under long time scales, and the other problem, what we call microchronological problem, solves the response of the structure under a single load cycle. And we made it time marching strategies in which basically we try to evaluate a small number of microchronological problems as possible as we traverse through the long time scales. And we can do this quite efficiently, as you will see here. This is another mesh objectivity verification. Now we're looking at a fatigue problem. So in this case, we're again looking at a cross-ply open hole CFRP laminate subjected to 95% of the ultimate strength fatigue loads. And we're looking at the evolution. So again, we have three different mesh densities that resolve the material and the structural scale. And three, we're tracking three different failure patterns: the 90-degree ply damage, delaminations, as well as the matrix damage in the 0-degree ply. Because the fibers are so much stronger, you don't see much of a fiber failure in these simulations. But because of the 90-degree, 95% of the ultimate stress is already imparted on the first cycle, you see quite a bit of damage developing already. But after that, what we're going to show is how the damage evolves under this loading condition as a function of load cycles. And this is how it shows. As you can see here, we're going in the order of around 320,000 load cycles. And what we're seeing is that the damage patterns are very similar to each other, regardless of the mesh density that we select. And also the specific crack growth and stiffness reductions are also quite consistent with each other. I did not even plot the case what you get if you don't use damage regularization, because you see immediate failure if you do not incorporate the regularization approach that we proposed. In addition to that, we can also essentially use these approach for different types of materials. Here we are comparing the behavior of a thermoset composite T300 914C to a thermoplastic composite, and they behave very differently. For example, as you can see here in the thermoplastic composite, you don't see the matrix cracks, 90-degree matrix cracks that occur and propagate. That's because of the mode 2 fracture toughness of thermoplastic composites being bigger than the mode 1 fracture toughness, which can be modeled directly with the type of multiscale approaches that we're proposing. With that, I would like to conclude. So we have established a multiscale discrete damage theory that can essentially capture the failure behavior quite accurately for both static and fatigue loading conditions. It incorporates the material microstructure into structural simulations. This is a novel approach in that sense. And it also is even though it requires and it models the damage behavior in a way that is diffuse at the macroscopic scale, because of our mesh size objectivity and our focus on mesh size objectivity, we do not see a significant mesh size effects in the model predictions. This also allows us, because we are going down to the scale of the microstructure and we're creating fracture-based representation at that microstructure scale, we are able to characterize or use measurable fracture parameters measurable from experiments and in describing the constituent damage models. And it also allows us to go beyond the more straightforward failure patterns and be able to characterize reoriented cracks and so on and so forth. There has been quite a bit of work and quite a bit of strides that we've already taken to realize this idea of certification, qualification, and design based on simulation, primarily based on simulation. The Air Force Research Lab and other agencies such as the Department of Energy and so on have made very significant investments in the past several years on this. And I think this is showing, I think we're fairly close to making a significant impact on the engineering applications of modeling failure in various different sectors, from aerospace to automotive to civil infrastructure. With that, I would like to end my talk, and I'd be happy to take questions, and I would like to thank everybody who listens to my talk, and happy to take questions now.
Bir saniye. Evet, şimdi dener misin? Şu an duyabilir. Oskay for this interesting and informative presentation. I have received a question, and now I will try to translate and ask you this question. Mehmet Ufuk Turan is asking, do you consider the time-dependent vibration feeding effect on cracking development under the effect of external loads only?
Thank you. Very, very nice and very interesting question. In this study that we have shown, we have not incorporated the time-dependent vibrational effects, but that is something that we have been addressing in a different fashion, under a different context. So there are two aspects I can see as important. So the frequency of the fatigue is naturally important, and higher frequency approaches, say, consider, for example, hypersonic systems or systems, even supersonic systems, you're starting to see dynamic effects take over and start having significant impact on the crack propagation and also the behavior under those conditions, right? The type of loads that we have done here has been more on the static, and the dynamic excitations have been fairly small. So if the excited dynamic frequencies are of the order or significantly larger than the size of the material microstructure, dynamic incorporation of the dynamic response is straightforward. There is nothing, you just add the inertial terms into the system, and the failure behavior would be able to deal with those kind of problems without having to do any additional work. We have not incorporated and tried to characterize that, but that is, something that we've done earlier, as I mentioned in other projects. When it comes to high cycle for basically high frequency fatigue, in which the frequencies are high enough that the waves that are propagating induced by either external roads or impact events and so on and so forth are in the order of or smaller than the size of the material microstructure, then you start seeing a significant variation of the stress fields near the crack tips and also the stress fields around the crack tip, and that starts to make significant impact on the behavior. In those cases, the standard homogenization would not be applicable, because the standard homogenization approaches do not allow for those interactions with the microstructure and the macroscopic waves. We have established models. I can basically, or maybe you can go into my webpage. They're listed there, that are non-local, that can capture those type of effects using non-local higher order homogenization methods. We go all the way up to 6th or 8th order asymptotic homogenizations to capture those behaviors. Or we have also recently addressed an interesting question, not in the context of fracture mechanics, but in the context of metamaterials, where we've established a spectral variational multiscale enrichment approach that allows us to capture the wave interactions with the microstructure in a very efficient and a very effective fashion, even for multiple wave nodes when the excited wave modes are multiple. So there are some slight differences depending on the frequency, but those are things that one has to take into account if one wants to do, focus on those vibrational effects a bit more.
Thank you very much. I hope the question is being answered. And let me check, is there any other question or not? Yes, we don't have any other question. Maybe I can ask a question, a simple one, not a technical one. Do you have an estimation how long it will take to use the information you gave widely in civil engineering practice or maybe structural engineering practice?
From the general perspective, they can be readily used in civil engineering practice when it comes to fiber reinforced components of civil infrastructure, right? So there are various different components that are starting to become available in buildings and other civil infrastructure, such as bridge abutments and so on and so forth, where one starts to use these type of approaches. And it is possible, especially when it comes to durability concerns, these type of approaches would be very helpful, and I think would be readily usable in those type of applications. The primary point is that we're really going to the performance limits of the system. If the structure is not operating near the performance limits, linear elastic analysis perhaps would suffice, right? Or standard fracture analyses may be good enough. But if one is looking at the durability aspects of it, fatigue aspects of it, I think those become quite important, and those could be questions that these type of approaches can be helpful, and I think they could be helpful in a readily available fashion. So we have been applying these approaches to larger structural simulations. They're not fundamental, right? So we do that, and there are various different challenges that come out of the Air Force and the Navy and the Department of Energy and other funding sources for us, and they are asking us to solve much larger systems. And the systems of equations that we're solving, or the systems that we're solving here, is efficient enough to address those type of problems. I don't see any significant roadblock in there for applicability when it comes to computational complexity. It is about finding the right problem and not necessarily attacking a problem that doesn't need this level of complexity just because we have the tool. I can't hear you.
Okay, now I'm turning on. Thank you very much, Professor, for this interesting presentation again. And dear colleagues, as we finished today's seminar, I extend my thanks to you all again for your participation on behalf of Turkish Chamber of Civil Engineers Istanbul branch, and we hope to see you again in the future seminars. Good evening to you all.